A discovery in science and also in particle physics is essentially when the new event is accepted by the community, by the peer review. And this is what makes the difference between a discovery and a claim. I can claim something important, but it will be really a discovery if everybody agrees. I mean, everybody, when there is consensus in the community about it. Part of this consensus is the peer review through one of the refereed journals, but essentially it's just the feeling that the community has about your claim. Then, clearly, quantification in physics is important. So when we have a result, we evaluate the probability of this result to be just something that is not new and is there by chance, what we technically call a background fluctuation, or if it's a new phenomenon. And so you hear some cases that 3 sigma is a strong evidence. 3 sigma is the probability of taking is 1 out of 1,000. And so yes, 1 out of 1,000 is rare, but when you compute the probability, you must really pay attention. 1 out of 1,000 when I compute tossing a coin is a very clear concept. When you put so many things as in a high energy physics experiment, when you evaluate the probability, you must be damned sure that you are doing all the bits and nits correctly. And 5 sigma is 1 out of 3 millions. That is even much more rare. But again, the same effect of having everything under control becomes even more difficult. But eventually, you see, the community is the best judge. If I make a claim and I can prove with nice plots that show what I am claiming, then the community will be convinced. The discovery in high energy physics takes time, but there is a big difference between the discovery of the Z and the discovery of the Higgs. The footprint of the Z, the papier d'identité of the Z boson, is very obvious. It's like you look in a cornfield and you see a poppy. You see it. I mean, there's no discussion. It's red among yellow things. It's a poppy, and the Z is like that. It was really something completely different from all the usual events that happens when you have a collision of, in that case, a proton and an antiproton. Higgs is much more difficult. You have to distinguish the difference between mice and corn. It's just you have to look at the details of the plant, and you have to ask an expert to see if a single plant, when it's young, is mice or corn. And so the search for the Higgs is more looking for a single plant of mice among many corn plants, and then looking for a poppy among corn. For sure, if we discover the Higgs, it will answer a very important question. The theory of the standard model is a very fine and special theory that has a very clear effect that we see experimentally. The fact that the gauge bosons, the one that bring the interaction, have very different property. The photon is massless, while the Z and the W have a mass around 85 GeV. Then this difference is something that is explained by the Higgs mechanism. The Higgs mechanism is a nice mechanism that explains how the standard model is born symmetric in the mass of the gauge bosons, and then eventually this symmetry is broken, and we have a light particle and two massive particles. And before the discovery of the Higgs boson, this is just a conjecture. So if we find the Higgs boson, we prove that Braut, Englert, and Higgs had the right conjecture in understanding how symmetry is broken in the standard model. It's a very important step conceptually in understanding our world of the microcosm. Then the Higgs may also give mass to the other particles. So this is another possibility, but is at a different level. I mean, we could be only the first one, but also the first and the second. So we could have that the Higgs gives mass to the vector bosons and also to the fermions. This depends very much on its properties. So what will be very important after the discovery is to measure precisely the property of the Higgs boson and see if they are conformal as in the standard model or if they are different, pointing to some new phenomena that we have not understood. Don't forget that there is something very important in the universe, that is dark matter, that we have not yet explained. And there are many theories in which dark matter and Higgs are coupled, like in supersymmetry. So maybe that what we have seen is a non-standard model Higgs that points to new kind of physics that can explain also dark matter. One aspect that for me is always important is to see how the larger physics community works. I mean, it's in Atlas and CMS we have at this moment really many hundreds of people working coherently to reach a scientific objective. So this is something that is peculiar to energy physics, not present in the other field of science, and I think that is also something very important for CERN.